Hello students. Today we are going to be covering Prof. Richard's favorite statistical lemma, the Neyman Pearson Lemma. This is my favorite proof and derivation, and you're going to see why soon. Let's first go through the description. So, suppose a simple hypothesis, HO, theta equals theta naught, is tested against another simple hypothesis, HA, theta equals theta A, based on a random sample y1 through yn, each from a distribution fyi given theta. They're all from the same distribution, with parameter theta. It's important that you state this. So, the likelihood function of the sample is L theta with parameter theta. The test that rejects HO at significance level alpha is the likelihood ratio test, which is equal to the likelihood of theta naught over the likelihood of theta A, less than K, where K is the value that will give you the maximum power. Now, any other test with significance level less than alpha will have a power less than the likelihood ratio. So any p-value test, any moment generating function, they will all give you a power less than the Neyman Pearson likelihood ratio test. Okay. Prof. Simon will be assisting me on the proof.
Hello everybody.
So, the proof of Neyman Pearson is fairly long, but I will break it down into 9 easy steps so that you can remember well. Okay. We're going to begin. Remember, because this is a statistics proof, you have to state everything you're doing in full sentences and explain yourself well. So, let's begin. The first step. To test a null hypothesis of theta equals theta 0 versus an alternative of theta equals theta A means to use a decision function dy is equal to 0 where the null hypothesis is accepted or where it's failed to reject, and 1 where the null hypothesis is rejected. So, first things first, you have to realize that this is a Bernoulli distribution.
Ladies and gentlemen, it's very easy to see this because what this is basically saying, you have a decision to make. You can either accept or reject the null hypothesis. 0 if it's accepted and 1 if it's rejected, with the probability P. Therefore, it's a Bernoulli.
Prof. Simon is exactly right. The second step is to state our significance level and our power. So, the sig level, alpha, is equal to the probability that O is rejected. You gotta reject those O's. So, the probability that O is rejected that O is true.
Hoes are always true.
Thank you, probably. Which implies.
Hoes don't get cold.
What? Hold up. Wait a minute. That the decision function is equal to 1. So,
Because we are rejecting it, guys.
exactly. So, the expected value at theta naught dy equals 1 is the significance level. The power 1 minus beta is equal to 1 minus the probability that O is accepted, given that the alternative is true, which is equal to 1 minus p dy equals 0. Therefore, the expected value at theta a of dy equals 0.
Prof. Berger, it will be dy equals 1 because it is 1 minus this, so it's the opposite.
I'm so sorry, Prof. Simon. I've disrespected
No
not
problem,
only
my boy.
statistics, but my favorite lemma.
It's easy to make mistake, but ladies and gentlemen, just be cognizant of what you've written down at the top.
The next step, we have to, what is the decision function? Your prof doesn't know, neither do we. What is it? It is the likelihood ratio test. So, let dy be associated with likelihood ratio test. This implies that when dy is equal to 1, k L theta 0 is less than, theta a is less than the likelihood of theta 0, with the expected value of dy equal to alpha. So, now you have stated that the decision function is associated with likelihood ratio test. What are we trying to prove now? That any other test with a significance level less than alpha will have a power less than the likelihood ratio. We only have one decision function, so we're going to make another one.
Prof. Berger, I'd just like to interject quickly and ask you please to just change this and bring the k over to the side, because what are we saying here? We're saying dy is equal to 1, so the null is rejected. Therefore, the likelihood that you get this is less than k times the likelihood of theta a. Or you can write it like that. Thank you very much.
Both are correct. So, let another decision function, we're going to call it d star, be associated with any other test.
Ladies and gentlemen, I just want to say a massive congratulations to the writing quality of Mr. Prof. Berger. Have you ever seen somebody write as neatly as this man?
Thank you, thank you. Which implies that the expected value at theta naught of d star y is going to be less than the expected value at theta naught of dy.
So ladies and gentlemen, what he's saying here is basically this part here. Because when you have a test that is less than or equal to the significance level, and what is our significance level? It's the expected value of dy. Okay? So he's basically stating in this section here that at a significance level less than or equal to alpha. So yeah.
Exactly right. So, step number 5. We want to show that the expected value at theta a of d star y is less than the expected value at theta a of dy.
And what that basically means is basically that the power will be less than, because theta a is the power as given over there. So that's basically what's going on.
Yes. So, why do we want to show this? Well, state your reasoning. With reason, when dy is equal to 1, okay, greater than the likelihood of theta naught, which further implies that 0. So, further, when dy is equal to naught, which is the complement of this, so we have what we want to show, and we have why we want to show it. So then step number 7 clearly is, this clearly is d star y k on theta a minus the likelihood of theta 0 is less than or equal to dy k l theta a minus l theta naught. So, going into step 8, by integrating, and I'll just quickly explain the next step.
So, ladies and gentlemen, we're going to take the integral of both of these functions, and that basically is going to look like this: d star y times k times your likelihood of theta a minus the likelihood of theta naught. Okay, I'll just demonstrate on this side here. The people, ladies and gentlemen, please remember that when you take an expected value of a function fy times y dy, you get your expected value of y there. Okay, so as you can see, you would times the d star y through, so it'd be k d star y times the likelihood of theta a minus the likelihood of theta naught, and therefore you would be left with this: the expected value of a d star y, you can just throw a k there, minus the expected value of 0 d star y again. As you can see, Brathberger over there.
Less than
Brathberger, you were correct. Keep the star.
my mistake. Okay. So, from here, it's fairly simple to see what we have to do next. We're just going to take the k, we're going to integrate out the k. Is less than or equal to E0 of d star y and we know that this step from over here, we'll call this 1, if I brought this E0 dy to this side, it would be less than 0. So we can just say that this equal to 0 from 1. Therefore, K E A D star y is less than or equal to 0. Continuing the proof up here. I know I said 9 steps. This was step number 9. I just like doing the brackets. So, continuing up here, we have a k less than or equal to 0. You can bring the k, 0 divided by k, nothing, so it's still 0. Then you have EA minus EA dy d star. So, bring this to that side, and then you have your final step. And thus, you have proven the Neyman Pearson Lemma. The power of any other test will always be less than or equal to the power of the likelihood ratio test.
Ladies and gentlemen, thank you for watching, and please like and subscribe.